All right, so let's look at number 21. So for 21, they ask us to find the limit as x approaches 0 from the right. So if we're approaching 0 from the right, those are the values that are larger than 0. So that's going to be this piece. So you can see we're going to take the limit as x approaches 0 from the right of negative x plus 3. Since that's a polynomial, we can do direct substitution and plug in. So that would just be negative 0 plus 3 or 3. Then they asked me for 22 to find the overall limit. So again, as we said on number 20, if you want to know the overall limit, you're going to have to find the limit from the left and from the right. We've already found the limit from the right, so let's take the limit from the left. So from the left-hand side, those are values that are less than 0, so I would be using this piece. And so I would have the square root of negative x. And so I'll plug in here and I get the square root of 0. Now, remember that if you get the square root of 0 as the overall limit, that limit doesn't exist. It will exist from one side or the other. So let's figure out if it exists from the left or not. So to begin with, we know that the square root of x looks like this. And we know that when you put a negative in front of x and plug it into the function, that causes a reflection in the y-axis. And so this is what y equals square root of negative x would look like. So as we're approaching 0 from the left, that limit does exist. It is 0. If they had asked me for the limit from the right, then that would not exist. The other thing that you can do is you can think about values that you plug in here. Like if you're plugging in 0 from the left, you're going to be plugging in like negative 0.9, negative 0.99, negative 0.999. As you do that, negative times a negative is going to be a positive. You're going to be able to take the square root of that. But if you were approaching 0 from the right-hand side, you'd be plugging in like 0.1, 0.01, 0.001. So for those values, those would all be negative and you would have the square root of a negative, which is not possible. And so that would be an algebraic way that you could determine which side the limit came from as well. In any case, we have figured out that the limit from the right is 3 and the limit from the left is 0. So since the limit from the right doesn't equal the limit from the left, then the overall limit does not exist at 0. All right, then for 23, you were asked to, on your separate worksheet, give the three-part definition of continuity and then use it to show whether the function was continuous or not at 3. So even though you were only giving a multiple choice answer on your separate worksheet, this is the work that I would have been looking for. And this is the work I would look for on your test. So the three-part definition is f of a is defined, the limit exists, and f of a equals the limit. What you just got for number 1 equals what you just got for number 2. But when you show me whether it's continuous or not at 3, you can't just state the definition. You have to show how that applies to 3. So first off, I'm going to plug 3 into the function and I'm going to see, is it defined or not? So if I plug 3 into the function, you can see right up here when x is equal to 3, I'm supposed to use this piece of the function, negative x plus 3. So if I plug 3 into that, I get 0. So yes, it is defined. It gives me a value of 0 when x is equal to 3. Then the second thing I want to do is find if the limit exists. So I'm going to look at the limit from the right and the limit from the left, which we've already done right up here. So from the right we got 0 and from the left we got 0. So we said that the overall limit did exist and it was 0. So that's what we've stated right here as well, that the limit from the right and the limit from the left are both 0. So if you had not already done this work up here, then you would need to, on the test, you would need to show me the limit from the left and from the right, that it would be equal in order to get credit for that portion of the explanation. All right, and then the last thing is we want to check to see if what we got for f of a is equal to what we got for the limit as x approaches a. And in this case, f of a was 0 and the limit was 0. So yes, they are equal to each other. So I've checked off all 3 parts of the definition of continuity. So yes, this is continuous at 3. All right, then for 24, it says on what intervals is the absolute value function continuous? So first off, if you just drew the absolute value function and you thought about where did I pick up my pencil when I was drawing that? Nowhere. So that means that it is going to be continuous everywhere. If you'd rather use the three-part definition, that's fine as well. So step number 1, is it undefined anywhere? No, because undefined is going to come from domain issues, right? From a 0 in the denominator or a negative under an even indexed radical. I don't have any problems with that. It's defined everywhere. All right, then I would need to find the limit from the left and the limit from the right. So remember that every absolute value is a piecewise defined function. So if what's inside the absolute value, x, is greater than or equal to 0, I'm going to get exactly what I started with. But if what's inside the absolute value, x, is less than 0, I'm going to get the exact opposite of what I started with. So if I take the limit from the right-hand side, then I'm going to be using this top piece right here. I'm going to be using x, plug in 0, and I get 0. If I take the limit from the left-hand side, I'm going to be using this piece. I'm going to be using negative x, plug in to a polynomial because it's well behaved, plug in 0, and I get 0. So the limit from the left equaled the limit from the right, and it's the same thing as I get when I plug 0 into the function. You can see right here when I plug 0 in, I get 0. So since f of a equaled the limit, then I could see that this is continuous. There was nowhere that I had issues. And again, we could also use the graph for that, as we said. All right, then for 25, on what intervals is this function continuous? So remember that we know that rational functions are continuous within their domain. So this is a rational function. So its domain is going to be everywhere except for where its denominator equals 0. So we're going to say all real numbers except for where x equals 0. And the same thing for this one, all real numbers except for where x squared minus 1 equals 0. So if we factor that, x squared minus 1 would be x plus 1x minus 1. So that would mean that x can't be a positive 1 or a negative 1. So it can't be 0, 1, or negative 1. So if we put that in interval notation, that's what it would look like right here. All right, then for 26 through 29, we were using the graph that was given. So for 26, it says, which of the following best describes the continuity at -3? So if we come over here to -3 and we look at our graph, there's a hole in the graph right there. That means that when x is -3, y is nothing. It's undefined. So the problem is the very first part of the definition of continuity. The function is discontinuous there because f of -3 is undefined at that hole in the graph. All right, then 27, which best describes the continuity at x equals +3. So over here at +3, you can see that it is defined when x is equal to 3, y is 0. But the limit from the left is +3 and the limit from the right is 0. So since the limit from the left is 3 and the limit from the right is 0, the limit from the left doesn't equal the limit from the right, so the limit does not exist. So this one is discontinuous at 3 because the limit does not exist. All right, then for 28, if we're looking at +4, so right here at +4, I can draw this without picking up my pencil, so that's the first sign that it would be continuous. But I also can say at x is equal to 4, y equals 0, so it is defined. And then the limit from the left and the limit from the right are both converging on the same spot. They're converging on 0. So since it's defined to be 0 and the limit exists to be 0, since f of a equals the limit, then yes, it is continuous there. All right, then for 29, which best describes the continuity at -2? So if we come over here to -2, obviously it's not continuous. I got to pick up my pencil to come up here because I've got an infinite discontinuity here. But it could still be continuous from one side or the other. So if I take the limit from the left, that's 0. If I take the limit from the right, that's infinity. And then if I do f of -2, that is 0. So anywhere the limit from one side is equal to the function value, it's going to be continuous from that side. So since the limit from the left was 0 and f of negative 2 was 0, since those were equal, it is continuous from the left-hand side. All right, then for number 30, we want to find where this function is discontinuous. So what I need to check for are domain issues. So I need to check where the denominator equals 0. So that's going to be at 4. And then I also need to check where the pieces of the piecewise come together. And so in this case, that's also going to be 4. So the only place I might have a problem is at 4. And so that's what I want to check. All right, so first off, every absolute value is going to be a piecewise defined function. So let's redefine it that way. So we could say if what's inside my absolute value, x minus 4, is greater than 0, it's positive, I'm going to get exactly what I started with, x minus 4. But if what's inside my absolute value, x minus 4, is negative, it's less than 0, I'm going to get the opposite of what I started with. All right, so if I look to see, is this defined at, remember as we said, you can't have 0 in the denominator, so this would be undefined at 4. So it's going to be discontinuous at 4. Now, let's say by chance that it was defined at 4, that was not an issue. The other thing we always have to check is where the pieces of the piecewise come together. So let's do that just for extra practice. So if we take the limit approaching 4 from the left, that would be using this piece down here. I can't plug into that because I get 0 in the denominator, so I'm going to algebraically simplify it. X minus 4 over x minus 4 would give me 1, so that would be negative 1 because of this negative out in front here. The limit of a constant is that constant. So the limit from the right-hand side, I would use this piece up here. And so that would be x minus 4 over x minus 4. So again, not well behaved, but I could simplify that down to be positive 1, and the limit of a constant is that constant. So since the limit from the left did not equal the limit from the right, we could say the limit does not exist at 4. So even if this had been defined at 4, it would not have been continuous at 4 because the limit didn't exist. When we rewrite this as a piecewise defined function, we were saying, you know, if what's inside the absolute value is greater than 4, or what's inside the absolute value is less than 4, typically we don't leave it written in that way. Like we would just go ahead and solve that to get x by itself. So I would just add 4 to both sides and get x is less than 4. Same thing here, I would just add 4 to both sides and get x is greater than 4. All right, then for number 31. If f of x is a piecewise defined function, why is it discontinuous at negative 1? So they're telling me it is. They just want to know why it is. So let's start with figuring out step number 1. Is it defined? So when x is equal to negative 1, y is equal to 6. So yes, it is defined. If we take the limit as x approaches negative 1 from the right and from the left, so when we're approaching from the right and from the left, we're plugging in values like negative 1.01, negative 1.001, negative 1.0001, and negative 0.9, negative 0.99, negative 0.999. None of those are equal to negative 1. So from the left and from the right, we're going to use this equation. So that's what you can see here. Neither of those are well behaved, so we would need to factor and cancel. So that would leave us with the limit of a polynomial, which is well behaved. I could do direct substitution, and then the exact same thing happens down here from the left. So the limit from the right equaled the limit from the left, so the overall limit does exist. So the function is defined, the limit does exist, but the problem here is what I got for 1 is not the same thing as what I got for 2. Where the function is defined is 6, and the limit is negative 2. They're not equal to each other. All right, and then for 32, the intermediate value theorem, remember the two things that we need to look for is continuity. So this is a polynomial. We know it's continuous everywhere. And then we want to look for a sign change. So since I'm checking the interval from x equals 1 to x equals 2, if I plug in 1, I get negative 1. And if I plug in 2, I get positive 5. So since there is a sign change there, we did go through 0, we did go through the root, we did go through the x-axis, then yes, there is going to be a root there. If there had not been a sign change, then it would have been no.